Yeah, good evening, Pratham.
Good evening, sir.
Yeah, am I audible?
Yes, sir, you are.
So, okay, I gave you two problem. Have you solved those?
I think I solved it right after the class.
Okay, fine.
Yeah.
So, we can move to the next topic, is it?
Yes, sir.
Okay, in the last class, I think I covered the combination of your capacitors, like parallel and series, basics of those. And
Sir, your voice is crackling.
is it fine now? Still cracking?
Yeah, it is still cracking.
Network issues. Pratham, is it fine now?
Sir, it's still
Happened?
like
Yeah,
I can
fine.
hear you, but it's not that good. In between, some words are not clear.
Okay, wait, let me check if it will change. Is it fine now? Still the same? Mm, wait, I'm not sure. Like it's
Like, फट रही है आवाज.
portray ना समझ लेना. नेटवर्क इशू तो नहीं हो सकता मेरा
I don't,
140 पे.
I don't think so. But I think we can continue with the class. It's okay,
Okay,
okay.
then it's fine. Okay, so actually, uh, okay, let's start with the Kirchhoff's law. Kirchhoff's rule. Better now. I'll prefer problem solving before going to the that. Okay, so yeah, I'm just giving you two problems. Yeah, I'm not sure this will. Okay, so the first problem is staircase problem. So the staircase problem mean to say it looks like a staircase problem. It's not exactly that thing. Problem one, you have given something like this. Okay, D, another D, and the last one is this. Area for each of them is given as a by 3, and this is also I think a by 3. Can take this also as a by 3. This distance is D. This is also D. This is also D. What you have to do is you have to figure out the net capacitance of this arrangement. Okay, and in between there's a medium that is air. That's
Okay.
other than this, it's very clear. Yeah, you can just solve the problem. This
Sir, in the meanwhile, can you check your microphone? It's getting worse.
it's getting worse. I can check it. Look,
And
wait. I'm not even using my microphone for the voice part. Let me check. Yeah, I'm using my inbuilt microphone. I'm not using. I'm checking that bill.
so we need to find the net what?
yeah, you have to get the net capacitance.
Net
Okay.
capacity. Okay.
Yeah. Okay, let's do one thing. Don't give me the final answer. Okay. Just tell me if what do you think about this problem? How many capacitors are there? Capacitors are there. You have to give me two things. Number
Uh,
of capacitors.
uh, your voice.
Wait, if I
I'm
remove it.
unable to.
Yeah, you have to give me number of capacitors and what is the arrangement? Is it series or parallel? Is it fine now? Still the same?
It's getting even worse.
It's getting even worse.
Yeah.
Okay. We'll see.
So it's good now.
Yeah. It's
Okay.
good now, still the same.
No, no, it's perfect now. Like it's totally gone.
Wait, the problem is I'm using the same microphones right now.
Yeah, I can see.
Okay, wait, let
Even
me see. If I use it again, I'm just changing my speaker.
okay.
Okay, and got the external headphone. Still, it's like it's lagging or still it's good right now.
It's clear, fully clear.
It's clear, right?
Yeah.
Yeah. Yeah. So have you solved this?
I was a bit confused. It's series or parallel.
Yeah. So that's the thing. Okay. Look, for the series or parallel, what happens is now every time we want given this condition. Okay. For parallel, how you have to identify whether two things are parallel or not. Just check out their both terminals. Okay. For example, if I have this capacitor, it's one terminal, it's another terminal. Take another capacitor, one terminal, another. If somehow both terminals are in contact, then you can say they are in parallel. Okay, then you can only say it is a parallel. One more thing, for example, this is, yeah, okay, if it is positive, it is positive, negative, positive, negative, they are in contact, then you can say it is what kind of terminal? It's a parallel
Parallel.
condition, right? If you see this diagram, I can say this is, I can say this is one capacitor, right?
Yeah.
So make it like this. Okay, let's do one thing. I can say this is one terminal. Okay, I can break it from here. Let's break it. If you break it, you will get another. Again, this connection, extend it a little bit, extend it a little bit. Got the three parallel capacitors.
Yeah.
You can write it like this. Another. A and B. So you can see this arrangement is having three capacitors, C1, C2, and yeah, C3. Okay. Even if you have to calculate the values, you can directly calculate right now. If you see what is changing in each of them, just your D is changing, right?
Yeah.
The area is still same for all. So your C equivalent will become something like epsilon naught A, because area in this is constant. What you are varying? D. In first case it is D. In second case it is 2D. For third case it is 3D. So this is what the problem solution is. Clear?
Okay.
Okay, let's do one thing. Instead of moving to the next part, we can solve these kind of some tricky problems. Okay.
Okay.
Yeah. So I'm giving you one more problem. Time. I'll just give you 2 minutes. Okay.
Okay.
And I don't want the final answer. Just let me know what you will be doing in this scenario. So the condition is given something like this: 6 volt. This is 4 microfarad. You can call it as 3 microfarad, and this is 6 microfarad. Okay. One, two, three. Basically, three capacitors are there. This is what it is given. First thing, calculate equivalent C equivalent. You have to calculate C equivalent. Second thing, you have to calculate um, V and Q on each capacitor. Third, you have to do is energy stored, energy in each and of total system of system. This is what you have to calculate. Clear?
Yes, sir.
So, and this is what the conditions giving. And you can assume like I have given the numbering as 1, 2, 3, so you can say the V1, V2, V3 also. Something like that.
Okay. So C equivalent will be 6 microfarad.
Yeah, it's 6 microfarad.
So what is written in the third part?
Third, in the third, you have to get the energy in each capacitor and total energy of the system.
Okay, in energy. Okay.
What happened? Okay, which step you are
But
in right now? The second or third part?
I found the wood. Is the total charge coming out to be 36?
Which one? The second one.
Total charge.
Yeah, total charge is 36. It's
Okay. And total potential is 12.
total
No,
potential.
it's 6. Yeah.
Potential same.
Yeah, yeah.
Can I solve it?
Uh, I'm trying to find the energy. I forgot the formula.
Okay, energy you can use half CV square.
So that only.
Yeah, you can use that, right? If you have something better, you can use it. It's all about the data, what data you have and which is handy.
Yeah. The potential for each is 4 and 2 for
Potential
V1.
for each is okay, 4 and 2, that's fine. Okay, for which one 4 and which one 2?
So your screen is not shared.
No. Okay, I can. Yeah, for which one it's the which one it is 2, for which one it is 4.
For the first one is 4.
Okay,
Second is 2.
and third one is by default it is 6.
Yeah. The energy will be 24, 12 and 72.
24, 12 centimeters. That's fine. If you add, you will get the total energy. That is more than okay.
Yeah.
That's the thing. So I'll just go through in a fast way. C equivalent, you must have solved it in an easier way. Like you can just simply do.
Yes.
Okay,
Are
this one.
all the answers correct? So,
Yeah, now it's fine. Okay. Look for C equivalent. What you can do? This is given in the series. This is given in the what it is. Okay, this comes in the parallel, so this will result you somewhere around 3 into 6 by 8 9 summation. You can just add this. Okay, you will get 3 to get the 6 answers. C equivalent. Clear?
yes.
Okay. For V and Q, what you can do is just take it like this, remove it from there. You have already got 24 this part, right? That is simple. Okay. For this one, you have already written that 6 for this terminal, is it?
Yes.
The rest part is you have to calculate for this one. And
These
you
two.
know, and you can use the voltage divider method,
Yeah.
right? So it's a simple thing.
Yes.
You can do like V1 equals to C2 and what is that? Total V divided by summation of your capacitance. So whatever it is, yeah, that is 9 into okay 6 into 6 by 9. So you will get something around 4. And here for V2 you will get it's 3 into V by 9. So you will get around 2 volt. Clear?
Yes, sir.
Okay, so that's the thing. And for the charge you can do what you can do. Okay, you have to calculate this also. Yeah, for the charge you already know what is the total charge.
The
You know this will be having maximum charge, right?
yeah.
Is it? because this has 4, this has 6, so I can say the total is 24 charge in between these two capacitors. Okay. Now the
Yes.
same charge will be at these two terminals also. The thing is, I have to calculate the how much each of them is having. Okay. So
Yes.
what you can do simply, Q1 is equals to whatever the charge you have to calculate. For which one you are calculating?
Q1.
Now basically, look, what happens is you have got the total. Wait, I just made mistake over there. This one was the configuration, is it? What is the total C equivalent for this one? We have got 6, right? For this one, how
Yes.
much? It is
Six.
what, 4. The value is 4,
Four.
right?
Yeah.
So
Yeah.
if I
Yeah.
ask you what is the charge, so you can say 4 into 6, 24. For this one, how much you are getting?
Yeah.
36, is it?
For C equivalent for the first two will be 2 microfarad.
For which one you are getting 2 microfarad?
The first and second, the above one for both of them, they are in series connection. No? So 1/3 plus 1/6.
Wait, wait. What I did? Yeah, okay, fine, fine. Okay, that is 2. So this 2 into 6 comes out to be how much? 12. Okay. So the total result in the total charge in this whole connection is how much? 36.
36. Yeah.
Yeah. So one thing you can do is you can calculate for both of them individually. What does meant by individually? You know this. Whatever the number of charges on this, the same charge is on this one also, right?
Yes.
Now, can I divide it into two circuits? Can I say I just have two circuits to solve,
Okay.
right? So I know the total is this much. I have to calculate how much is on this one and how much is on this one. So this is what I have to calculate. So I can say the Q1 is nothing but whatever the charge, like whatever the potential net capacitance, that is 2 into the total charge 36 divided by the summation of net capacitance. What is that? 6. You will get something around 8. 8, right?
So
No,
12.
no. Yeah, it should be 12. It should be 12 microcoulomb. That's fine. And for Q2, how much you are going to get? 4 into 36 divided by 6. Again 24. Got it?
Okay.
Wait. I already had this answer. Why I did this thing for no reason? Yeah, from this is how I calculated 36, right? When I said this is Q1, this is Q2. Okay, so this was Q1, so it will be on the both sides. That is. Energy, is it clear or should I do it
It's
again?
yeah. It's
Right?
easy. Yeah.
It's like C1. You already have V1, Cn, so you can directly get 24. Like for one is 12, for this. For second is it is 12. For one it is 24.
Yes.
72. These things. Just a second. So yeah, I can go with right now. Kirchhoff's law. Okay.
Okay.
Hmm, lecture number. So the Kirchhoff's law. You can study Kirchhoff's law in this topic also, and that in detail it will discuss in the electric currents. Okay,
Okay.
when we'll be solving the circuit. In case
So,
of capacitors, yeah, what happened?
so I don't think I'll have to take classes for current electricity.
Okay, then it's fine if you don't have to
Because
take the classes.
yeah, because it's easy and able to understand everything in class.
Okay, then so we can skip that. Okay,
Okay.
So I'll not be dependent on that thing. I'll cover this capacitance part. Okay.
Okay.
So the look for resistance. Okay, you have already done electric current, right?
We have just started after
Okay.
completing capacitance.
Okay, so fine. Look,
Okay.
for Kirchhoff's law is basically based on two rules. One is potential difference, another is current or charge. Okay. If you see in capacitance, we are working in the charges. So for capacitance, it is based on the charge. For resistance, it is based on the current. Okay.
Okay.
So here main discussion will be potential difference in charges. Kirchhoff's rules used to determine potential difference and charge on plate of capacitor. Okay, plates of capacitor in circuit. It's clear. For example, okay, this is one thing, and what I can do. Two rules. I'll just write net potential difference around a loop is zero. Okay. Also, at any junction, net charge is zero. Clear? What does this mean? If you have some condition like this, you can also assume it in this way. Let's say three capacitors are like this, okay, and they are set up in this way. This is the junction we call, right? So Q1. Let's say this is a minus. It will be minus Q2. If you are saying this is Q2, so this will be minus Q2, and you can call it as minus 3. So what will happen at this point? The net charge, okay, net effect of this charge at this junction will be sum out to be zero. So you can say Q2 plus Q3 minus Q1 equals to 0. Okay,
Okay.
this is one thing. And about the first loop, uh, yeah, for the first one, you can say if some circuit is given like this, you have too many resistances are there, capacitance are there, something like this. If you just turn around from, let's say, from started from here, and you come up again at this point finally, now you will get the net potential to be zero. Understood?
Yes, sir.
From where you have started, if you come back to same position, then you will be getting zero. You can't say okay, you have started from here, you are ending here, and you will say zero. No, it is not the case. You may get some value over there. So these are two rules. The proper definition of this is a part of your current electricity, because there we properly study the junction rule and the
Yes, sir.
loop rule. Okay, it's mostly based on your energy conservation. You can see we are conserving the energy in this case.
Yes, sir.
Something. Okay. Mm, so let's take an example for illustration. Something like this can be made. This is one more capacitor, let's say, and this one more. Okay. So this is a combination of capacitor is given to us. We are interested to calculate some values over this. So three I can say, four I can say, and these are okay. Let's make these batteries. We need batteries also so that they can be charged or uncharged.
Okay.
Okay. So you can call it as E1, E2, E3. This is the configuration given. This is also connected one. So we can say calculate charge on C1 and C2. Okay, this is what can be given to us. Now if you see carefully, in this configuration I don't have a direct method because batteries are connected in some different ways, right? I can't directly do a q is equals to some c equivalent v, right?
Yeah.
Because for this battery I don't know, like I need a proper equivalent, but I can't do because I can go here and say okay this is series, but further I can't say it is in the series also, because for this I have to solve this thing first. Clear?
Okay.
So how we can solve these kind of problems? In the For these the Kirchhoff's law comes into the picture. Okay,
Okay.
so what we do basically, we have to identify one isolated reason. Okay, isolated reason basically where you will having only cells. Okay, so can you figure out some isolated reason here?
Where we have only cells.
Cells basically.
E1, E2, and E3.
Wait, wait, wait. My voice is clear or still it's lagging?
Ah, it's fully clear.
It's fully clear, right? Okay. Look, isolated reason I can say, okay, assume some reason is there where you can start traveling from one point, okay, and like can travel any point in an independent manner. Okay, so that will be your isolated reason. I will take an example and will let you know this. Okay, so the some isolated reason I can say, just check the C1 and C2.
Okay.
Okay, and let's see what it can be. C1, C2, C3. You can see I can think of some operations at these points, right?
Yeah.
Remove it. What else I can say? Check this one.
Yes.
Right? Can I include this also? Okay, let's not add three batteries. Okay, let's make it C5. It will look better for us to understand. Now, can I say this is also one reason?
Okay.
Isolated mean to say I just wanted one at least at a max inclusion of one voltage. Okay, one cell.
Okay.
So that's the thing. In similar fashion, you can say like this is also kind of isolated reason.
So, but if we include C5, then even will automatically be included.
Wait, wait. This is not the C E1 E2, right? It's just a C5.
Yeah. So if we include C5, then even will also be included.
No, no, I'm just including this part, right?
So even won't come into line.
Yeah, no, I'm not including it, right? I can
Okay.
include this part itself also. It's up to me like whether I wanted to take this into consideration or not. So I'm not taking
Okay.
it. Okay. Let's solve this. How we can do? So first thing is conservation of energy. Okay, we will go with the conservation of energy. What we can do? We know all the charges are conserved, right? If due
Yeah.
to some battery, some charges are going to flow, maybe from this charge, X will leave. Possibility is there that X can go and accumulate of this point. Maybe some part of this goes at there, goes to this one, goes to this one, goes to this one also. Okay, so these
Okay.
possibilities are there. So at the end of the day, I know whatever the charge is total, that is going to be conserved. Basically, energy is conserved, something like that you can see. Okay, one more thing, you can see that the these cells are there, is it?
Yeah.
But one thing to remember, these cells don't provide extra charges. Provide extra charges. So this is one thing to be noticed. Okay, whatever the charge are there earlier, we just have to go with those things. So simply what I can do, yeah, they don't provide your charges, they can provide you flow. Basically they will allow you a path for a proper flow of the charge. Is that clear?
Okay. Yes.
Okay, so what we have to do, we have to get the algebraic sum of all the plates in any independent reason, you can say, or isolated reason, which sums out to be 0. Okay,
Okay.
so I'll just mark it up here in this picture. Let's say this is Q2, this is Q1. Okay, let's not go in this way. See carefully.
Mm-hmm.
Um, One thing is clear, that all the charges are supposed to be same, right?
Yes.
What can be included in this? Okay, let's say this plate is minus Q1. It can be, you can say it is minus Q1, right? Because this is minus Q1, so you can say this is connected to whole thing, so this is also minus Q1. Can I say this?
Yes.
This plate, if I am saying this is minus, like for the C, with respect to C, if I am saying C2, this is minus Q2. So can I say this is also minus Q2?
Okay.
Similarly, if okay, just a second, like this. Yeah, this is one thing. Okay, and if you are saying this plate is minus Q2, so you have to say that this plate is also Q2. Is it?
Yes.
Or similarly, here you have to say Q2, Q1. Is it clear? Have doubts still? Like some doubts are there.
I think it's clear. It will get more clearer with practice, I think.
Okay. Uh, let's do one thing. Let's leave Kirchhoff's law for now. Okay.
Mm-hmm.
Let's do the dielectric part. We'll do the dielectric first, complete that dielectric portion, then we will come back to the Kirchhoff's law. Is it clear?
Yes.
I'll add some pages. We'll remove this part. I'll take some good problems from which we can practice this Kirchhoff's law part. Okay.
Okay.
Questions. Okay. So look, in the previous chapter for the electricity, we have already studied what is dielectric, right?
Yes.
So dielectric. These are kind of non-conductors. Okay, basically these are kind of non-conductors. What they can do, they can provide some polarity. Okay,
Yeah.
conductors, or you can say they are non-conductors up to certain electric field, certain value of electric field. Okay, if field goes beyond the limit, if field goes beyond the limit, the that is, we can call it as dielectric strength. Okay,
Okay.
what is the strength? The limit till which till which it can withstand with that particular electric field. Okay,
Okay.
after this limit, dielectric loses its insulating property. Okay, it goes into conducting nature and starts conducting. But one thing is clear, that it won't be able to conduct as a conductor. Okay, for example, in the initial case I have box all the, let's say these are the pairs. Okay, these are the thing we something call okay, these are some alignments. If they goes into straight thing, now then they are good conductors. Okay, so
Okay.
in general what happens, they are situated like this in a very random order, you can't even consider anything. Okay, but what happens at a certain level, after providing certain level, all these signs goes like this. Okay, so
Okay.
this is the polar pairs you can call. What is there? I couldn't remember that. So that is the thing. This is a dielectric. This is just about the dielectric, not the dielectric constant which we studied in the previous chapter. This is what the meaning of dielectric. For that dielectric, we have something called constant. So
Okay.
that is called as dielectric.
Dielectric constant.
What is that constant? Okay, when placed between capacitor. Okay, what do you think if you place the dielectric in between capacitor, will capacitance increase or decrease?
The when dielectric is placed between the capacitors, uh, I think it will increase because it will increase the polarization.
Yeah, it will actually increase. If you see, this is the different nature. In cases of force, when you introduce a dielectric, what happens in that cases? Yeah, the force between charges decreases, right? But here the
Yeah.
capacitance is increasing. Okay, the
o-
capacitance gets increased.
Okay.
So I can say when placed between capacitor, capacitance increases. So you can say the ratio of increased capacitance with dielectric to without dielectric gives you constant. Okay. Earlier we don't know what is the value or what is the constant. By some experiments we figure out that if you place a particular amount, particular nature of dielectric in between two plates, okay, then what
Mhm.
happens? Um, the value increased by a constant. Okay, whatever the capacitance has been increased, this is increased by a constant value. So this k, we write the dielectric constant with a k. C ck divided by c. This is with the dielectric. This is without the dielectric. Okay, this is how we can write it. Or instead, you can say it to be the capacitance, and this is without dielectric. Basically, not in the air and something. Okay. Now the part is how the electric field work inside it. Look, just assume I'm talking about this conducting nature. Okay, this conducting nature.
Okay.
If you see, what is capacitance? Capacitance. It is nothing but E epsilon naught A by D, right?
Yeah.
Just assume this is my parallel plate, right? If you see, this is the distance between them. When I include dielectric, what happens? There's some polarization happen because polarization will always happen. If the dielectric, instead of this you plate a conducting plate, what will happen? The number of positive charges are there, same number of negative charges will come up here.
Yeah.
Same number of negative, like these positive, if these negative come up here, this will become positively plate, this becomes negative. So you can see
Negative.
now what you have got here. You have got two plates. It is like this condition with a different value because D has been decreased by a very huge margin, is it?
Yeah.
But when when I'm putting dielectric inside it, this is
Uh-huh.
not going to happen. The reason is, I told you again, the dielectric is of insulating nature, right?
Yeah.
So whatever the increases happen, that depends upon how much it can get polarized.
Okay.
Okay.
The
For
power.
example, this original plate was having 1,000 charges. For a dielectric, it is not possible to have again 1,000 charges at this plate of a different polarity. Is that clear?
Okay.
But it because we are providing in high electric field. Okay, for example, this is your plate. Okay, this is another plate. Electric field is in this region, right?
Yes.
When you put in dielectric, what happens? all the negative, let's say they are those who are this side, they wanted to go this side, okay, they will tend to move this way, they will
Yeah.
tend to polarize this side due to this nature, due to this high electric field. In that case, what happens? This polarization of this dielectric happens. Clear?
Okay.
If I ask you what is the net electric field inside, so I can say one thing. Let's say this is the initial electric field E. Okay, I'll just end up discussion till here, and we have not discussed anything today. I won't send you any PPT today. Okay, okay. I'll continue from here. So yeah,
Okay.
this is the thing. Let's say I have included a dielectric. Now I told you some amount of charge is going to get polarized. So you know this is negative going to happen. This will be positive. This is positive going to happen, right?
Yes.
Okay. This was the original thing.
Yes.
This is so. If you see carefully, I have got another electric field.
Uh-huh.
So what is the net electric field inside? E minus E polarized. Clear?
Okay.
Okay. E minus E polarized. This is what I have got. And I can tell you one thing, that whatever we have got, the final electric field in between, that is half of the value, half of the mean to say E final. Whatever we have got, that is E by K. Clear?
Okay.
That is the reason in dielectric this happens. Okay, you will get to know why in if you put the things into the dipole, why the force get decreased. Okay,
Okay.
this here, from here you will get the bit reason. I can okay, let's see. This is a positive charge, right? This is a
Yes.
negative charge. So there's a force between here to here. Then what happens now? Let's say this you put it into the water. What will happen? This will somehow get surrounded by some of the negative charges. Clear?
Clear.
This will get surrounded by some of the positive charges.
Yes.
These bundle of these negative positive creates an this kind of electric field. That's the reason the net electric field get decreased.
Yeah. Yes,
Understood?
sir.
E net gets decreased by some huge margin. And you know what is this net value? This E net is nothing but the total divided by the your constant K. Clear?
Yes, sir.
So here you can also say this E final, basically E net is nothing but E by K. It is equals to E minus E polarized. So you can say E polarized is nothing but, you can take E common, K minus 1 divided by K. Clear?
Yes.
This is what the polarized is. So that's the thing. And if you say rest of the things are same, you can also calculate how much charge has been polarized, because you know whatever the electric field you are having, it is due to, right now it is only dependent upon the charge, because rest of the r distance and all things are constant, right?
Yes.
So can I say this polarized charge is directly proportional to E? Like what charge was E was directly proportional to charge. So in this case, I can say this polarized charge is nothing but total charge, whatever the initial was, your dielectric minus 1 by K. Clear?
Yes, sir.
Now, if it is a what you can say, if it is in the air, okay, you know what is the dielectric of air? K is equals to 1. Put the 1. What is the polarized charge in the air? That is 0. If the charge polarized is 0, net electric field in opposite in the air comes out to be 0. That's why we say whatever the field is, that is due to the charges itself. Okay.
Okay.
So that is for the today's class. I'll end up here because my next class is there.
Yes,
Okay.
sir.
I won't send the PPT today. I'll continue from this part itself in the next class. Okay.
Sure, sir. And
So
sir,
that's all
how many more classes are there?
for this chapter.
Yeah.
Okay. Maybe okay. In the next class,
Second class.
in look in the next class, I will done with this part. Okay, the dialectic and all.
Okay.
And look, if you can take the morning class, for example, maybe 3, 4, or some other time, then I can end up this chapter in the next 1.5 hour.
Sure, we can do something on Sunday because tomorrow I'll
Sunday I'm not free. Sunday I'm not free.
sure, because tomorrow I have Ali. So That's
Okay, we'll see. Okay, I am giving you one problem. If you are if you can do that part, then we will cover up one more topic. Okay, so that
okay.
is spherical capacitor.
So I thought, didn't we do this earlier?
Yeah, we
Or
have
we
done
did that earlier?
4 pi epsilon not r, right?
Yeah.
This is not that. Here, what happens? I have another one more circle. In the previous case, I just have charges outside, okay, and I was assuming that one another bigger body is very high, so we I was not assuming that thing. Right now, I have two cavity. One is having radius r1, another is having radius r2. Okay, and it's up to you whatever you want to assume. Like you can assume the charge on this one positive, negative, negative, positive. Okay, this is what you can assume. So yeah, this is the problem. So you have to calculate capacitance of this capacitor.
Okay.
Okay, try to do this. I'll just tell you one thing. The same charge on this and charge on this will be same. Okay, so you have to go with the density part because you know the density will be same because
Yeah.
density is nothing but charge by area. So this is what you can do.
Okay. Okay.
Okay, so that's a hint. You can just solve this one if you are done with this. Okay, try one more thing. There is nothing. Cylindrical capacitor.
Okay. Cylindrical capacity.
Here what happens? Electric field will be either you can take this way, either you can take inside. It's up to whether which charge you want. If you are taking positive here, if you are taking negative here.
Yes.
So you can see your electric field is going from this point to this point. Some charges are there. You know how to calculate this. C equals to delta Q divided by what is that? Delta V, right? So you have to
Yeah.
get the V is equals to E dot dl. Okay, this is what you have to do here. If you do this, you'll get the answer.
Yeah.
Okay, so yeah, that's all for the today's class.
Thanks.